Okay, I'll do the first part here, and then I'll hand over to Kai afterwards to give us a demonstration. So this session here is on data analytics with SNOMED. So in this afternoon, we are going to explore querying data. We did look at that in before lunch with learning a bit about expression constraints. So this afternoon is about how that can be supporting data analytics, and then we are going to also look at how to using a terminology server and to enable these features. So we'll do an introduction. I'll do that now, and then we're going to give you three scenarios, show you three scenarios, data analytics scenarios, using a tool, an open source tool that we've developed. So what is data analytics? Just to have a common point of reference. Well, it's the discovery and communication of meaningful patterns in data. And just by this, we've spoken a lot about meaningfulness today already. But the fact is that what is meaningful is very subjective, right? What is meaningful for me may not be meaningful to you. It really all depends on what you need. But data analytics can be performed on an individual patient. So you can imagine creating extract all the diagnosis of a patient to provide some overview of the history, maybe exploring specific tests, results of tests and investigations. That's also kind of discovery of meaningful patterns on an individual patient. A more common type of analytics or a classical interpretation is that you do it over a population to compare different people within a population. You can do analytics also on a larger scale where you want to compare across organization and you want to do analytics across maybe a number of hospitals. And you can also do it internationally or globally. You can do analytics over population in different countries. So data analytics is a broad definition and a deep definition in that sense. These shows three overall categories of data analytics in healthcare. So one objective is to do analytics to support the patient care and treatment. Another type of analytics is on a population, where you want to monitor a population trends over time, or for research studies to do some studies, trials to provide evidence. For the first group, for patient care and treatment, the types of analytics that the reason why you would want to do analytics would probably be to support the process of treating patients and caring for patients. Like, if we do this type of treatment, what happens to the patient? What is likely to happen based on the specific individual, the history, and as we go in more and more into precision medicine, many factors will actually contribute to the proper assessment of specific treatment options. For population health, it's what are the trends within a population to understand better what we can do to maybe increase the general quality of healthcare in a population. And within research, it's often questions such as causal effects. So how can we improve the efficiency and quality of the care provided? And it is a kind of a cycle, right? The data that is collected for an individual patient contributes to the population health monitoring, which again contributes to the research. And the research, it's similar to the knowledge cycle I showed you before. So this should be familiar to you. We have spoken about the semantic network and how SNOMED CT is one of these. But let's now see how this semantic network is useful for querying. And you already know about this from the session before lunch. But let's look at the different types of queries that are possible. the subtype hierarchy. So a concept such as pneumonia in SNOMED CT has many supertypes. Here you see some of them. It's dotted lines because we have removed many of the intermediate ones. But you can see from this that pneumonia is a type of disorder of lung, it's an inflammatory disorder of lower respiratory tract, and so forth. So these are only the ISA relationships that we see here. And here we have other concepts, colitis, appendicitis, bronchitis, they are all, if we just look at the ISA relationships, they are all linked to the concept, top-level concept disease. It's not a top level, but it's a high up in the hierarchy concept disease. Yeah. And we use this subtype hierarchy. And this is where you recall the descendants of symbol from the expression constraint language. This is essentially what it does. What are the descendants of inflammatory disorders? Well, we use the ISA relationships to traverse down the hierarchy and find all the subtypes. And this is also the way that we can use these ISA relationships to identify common denominators. That a common denominator for these four concepts is that they are all inflammatory disorders. And that's useful for data analytics. So imagine we have a group of patients being identified with or diagnosed with these different concepts. And now you want to ask, can you tell me who have a respiratory disease? Then we find the concept respiratory disease. As we identified it in the browser, we did a search for respiratory disease. And we say, give me all the subtypes. Apologize. Give me all the subtypes. And then you can match against the data in your data store to identify the patients. Another question is, this is more in the decision support mindset where you want to have the terminology help you answer question. Does this patient have a lung disorder? Well, then you identify the concept lung disorder, but the descendants of lung disorder does not match the concept that is the diagnosis for this patient. So because that's not a type of lung disorder. So no, this patient does not have a lung disorder. So that was an example of how we can use the ISA relationships. So why those descendants of and single less than signs, why they, and also the greater than signs, why they become powerful, because we can use those ISA relationships. Now let's look at the defining properties that you already know a lot about. So the finding sites, here we have a set of concepts that have specific finding sites. They also have associated morphologies, some of them inflammatory morphologies, others dysplasia, fibrosis, abscess. So these defining properties can also be used. So we want to identify people with a disorder located in the colon structure. Then we can use the finding site attribute. If we want to identify people with a fibrosis morphology, we can also do that looking at the morphologic abnormality for these disorders. So what these slides shows is that if you know what questions you want to ask, then you can actually transform these into, you need to identify what are the concepts we need then. So in order to find people with a respiratory disease, we want to find all concepts in SNOMED that represents subtypes of respiratory disease. If you want to find people with a disease located in the colon structure, then we need to find all diseases that have a finding site of colon structure. So this just shows that you need, in order to go from a question, you need to do analytics with SNOMED, you need to then go through the thought process of thinking, what are the concepts we need in SNOMED? And then from there, you are able to define the query you need to specify. And you can do that using the expression constraint language. And this is quite essential because it doesn't matter just to sit down and construct an ECL. You need to know why that ECL match what your criteria, why this is a good expression constraint for your purpose. So this is just the principle of ECL. I'll just skim over that. But this shows the technique of doing patient analytics. So you have a terminology server with SNOMED. supporting ECL. And then you have a separate data store with your patient data. So you execute an expression constraint against a certain substrate on your terminology server, and that produces an expansion. And that expansion you then compare to the appropriate field in your data store, patient data store. So this is also an illustration of that you can have it separate. You don't need to have all the terminology services supported by the data warehouse. You can have it separate, a separate terminology server where you do the ECL to produce the expansion, and then it's the expansion you compare to certain parts of your data store. So this was the background for data analytics, and let's now start to look at some examples that actually do this with SNOMED. The first example is the population monitoring. So if you recall from this morning, this is the scenario we're going to try now in our demonstration, where you can imagine that we have gathered SNOMED CT data in a repository from various organizations, and now we want to explore this. So it's the population health monitoring. So looking at what are the trends within this population. And we can do this is the scenario where we want to summarize and aggregate health-related information. We want to identify health trends and patterns. And why is that useful for example, a country or a hospital? Well, it is to be able to monitor incidences and prevalences of diseases. It's to monitor effects of national or local programs and initiatives. It's often also to balance and prioritize health-related costs. So it's also a financial incentive. Are you ready, Kai? I'll hand over to you then. You can take the screen.
Yeah, I'm running on my mobile connection because I had a firewall issue accessing this website, but here we go. Do you remember which slide you're on, Anna?
Yeah.
Yeah. Okay, great. Great. I'm catching up. Okay, so we're going to have a demonstration of how we can measure the incidence rates of various disorders on a synthetic data set. So we've generated a population, a small population of around 1 million people, and the prevalence rates of disorders are based on the national statistics from Denmark, which have been published over a series of years. So I'm going to switch now to our analytics demonstration tool. It's an open source project. It's like a Java web application. It's available in the IHDSDO GitHub. It uses FHIR terminology services, which I'm going to do a session on straight after this. And it has an Elasticsearch data store. So we can load patients into this tool in 2 formats. One is a FHIR patient record format, using bulk exports. And there's also a native like CSV format. We've got a generator for that for synthetic data. Although this is a demonstration tool that we use, and it's fairly basic, I suppose, it does demonstrate some of the features of ECL, and we have used it with real data in a few settings in Europe. So we know that it works well on real data, not just synthetic data. So we're going to start off with the longitudinal comparison. There's 3 sort of main functions that this tool does, and we'll go over all of them, but we're going to start with the longitudinal comparison to show, incidence rates and trends over time. So I'm going to pick a data set here, which is the Danish National Statistic dataset. And this form allows me to build up a report or a study. And to start with, I will specify the cohort of patients that I'm interested in. And there's no real prerequisites here. I want everyone in this data set. So I'm not going to do any refinements of the selection. I'll include everyone. The time period is a long time. It's a 20-year study starting in year 2000. And I'm going to end it in the 1st of 2021. That's the end date. We can pick granularity here. Basically, we're going to generate a graph or a report, and yearly granularity is fine over this 20-year period. There's various outcomes that we're interested in measuring. I'm going to put them all in here. So this allows me to search for various SNOMED concepts. I can say which type of outcome I'm interested in, be it findings, disorders, procedures, observables, or drugs. Most of them are disorders, but I'm in the habit of selecting clinical findings. So we're interested in asthma, dementia, COPD. Oh, yeah, I will. As we build up these findings that we're interested in, because it's a demonstration tool, we've got a tooltip here on the right-hand side that shows the ECL which will be used. So the double less than symbol shows that asthma and its descendants will be selected for this report. And in this synthetic data set, we haven't used any of these higher level concepts like asthma and dementia. We've generated the data set that uses all the descendants of asthma to try and make it more realistic, more detailed. I've got two more here. I've got osteoporosis and the two types of diabetes. Remember we talked earlier about inactive concepts, and I said if you have a long, if you're recording data over many years, it's very likely that you're going to have patient records that have inactive concepts in them. When you're doing a longitudinal study like this over 20-year period, it's going to be absolutely essential not to rely on the hierarchy to find all types of asthma, because the inactive concepts are no longer part of the hierarchy. They're not included. So this ECL won't find them, and those patients won't be counted. So there's a feature of ECL, and there's a button here which, to aid the demonstration, we click the button and it updates the ECL, and it puts this angle brackets at the end, and it says plus history. And what that does is it includes the inactive concepts that are linked to any descendant of asthma. I'll talk more about that in slides in a moment. So we're ready to run this report. I click run, and it starts to generate over the years, pulling the data from the API. And this is a nice longitudinal view, and really the purpose is to show trends over time. So we can look. We've got the diabetes 1. This is incidence rate, remember, so it's the number of new cases per year, and it's balanced based on the population size. So diabetes 1, type 1, nothing's really happening. It's just going along very steadily. Type 2 diabetes is kind of going up. It's towards 2010, and then it's coming tumbling down. We've got a few disorders here which are kind of linked. We've got asthma, and we've got the chronic obstructive pulmonary disease. Now, these are both in a nice downward trend, and we believe that's linked to national strategies in Denmark to try and reduce smoking. Initially they started reducing smoking in public places, I think around here, and more and more sanctions were put on smoking. And we can see that it's having, you know, a really positive effect on the incidence rate of asthma. It's coming tumbling down. Is there any questions before I move on to the next scenario? Oh, I need to remember. The question is, do we have a forecast functionality so we can see into the future or predict what the trends are going to do next? No, in this tool we don't. No. But yeah, it's an obvious thing to have in a tool like this, isn't it? Do some forecasting, see what's happening ahead of time. Yeah, so I suppose in this type of analysis, you want to know what's going to happen, you know, likely to happen in the future, because maybe that will, you know, change your healthcare strategy. You know, implement more education, or it depends what it is, but you know, divert funding, create new projects to try and tackle things that are coming out of control. Yeah. Of course. Yeah. Great idea. All right. We're going to keep going. We've got 2 more scenarios. So these are a couple of slides about national registries. So it's quite common to, you know, in Europe to have national registries for cancer, or, you know, there can be many registries in each country. And it's common to base them on a statistical classification like ICD. And there's some benefits of this because, you know, ICD codes change infrequently. It's already, you know, higher level categories, which are kind of easy to report on. The codes in a classification like this don't have any overlap, so it's easy to not have, you know, double reporting in different categories. So that's one approach. Another approach that we're seeing increasingly is to have national registries based on SNOMED CT, you know, particularly for disease and mortality. Obviously, SNOMED allows you to do, you know, selective and explorative analysis of data. You could probably be more granular. Of course, you can, you know, use the whole SNOMED hierarchy, and you could do, you know, very broad analysis like all types of asthma, or all types of pulmonary disorder. So there's a lot of flexibility. Things aren't pre-categorized. You can choose your level of aggregation or reporting. I've got some the kind of comparison of approaches summarized here, but they're in the slides. So the third approach is to have a hybrid solution where the information is recorded in terminology like SNOMED CT. You know, obviously at the point of care, that's most relevant, but it could be sent up to a national registry as SNOMED CT to allow, you know, some flexible analysis. But of course, using the maps, it could also be represented as a statistical classification, so that you could, you know, keep going with ICD-based reports at the same time. You know, have the best of both worlds. Okay, we're moving on to the feature of ECL to allow us to query historical data. We've got some examples here where a few types of asthma are recorded over the years. This Hey asthma may have been recorded on the healthcare record in 2005. In 2011, this concept Hey asthma was actually made inactive. And we've got more examples. We've got an acute asthma here. Could have been recorded in 2010. In 2021, it was made inactive. So if a clinician needs to identify the patients, all the patients that have been diagnosed with any type of asthma, they probably, you know, they could use something like ECL to find what are all the codes for asthma. And they would only actually find this patient that's got Baker's asthma because it's the only concept that's still active. So it's the only concept that's still in the hierarchy, and it's a descendant of asthma. So that's obviously a problem, and it's something that various countries came to us. I think it was around 5 years ago, saying this is a real problem. What do we do? ECL doesn't cater for this. So we updated the ECL language and specification, and the terminology servers to allow for this. It's called a history supplement, where we can say, give me the historic concepts as well. And you only want to do that in some situations. When you're creating a value set, or if you're doing anything with data input, you don't want the inactive codes. But if you're doing analysis, particularly over many years, obviously they're needed. So once the history supplement is added, we get a selection that includes all the active and the inactive concepts. So concepts, for example, this allergic ineffective asthma, they can be made inactive for various reasons, to correct errors that have been made in the past, to keep update with clinical knowledge. Sometimes duplicates are found. Sometimes from a national extension, they find that the concept has been created in the international edition, and then one will be made inactive. But it's important to, retain access somehow to these inactive concepts. And the way, oh, there's a question, go on.
The possibility of making queries on historical data this way, is it based on logical definitions of inactivated concept? Because I learned it when a concept is inactivated, it loses its logical definition. So is it based on, okay, that's here, with the same as, and okay, thank you.
Yeah.
Yeah, so the problem with keeping a logical definition when you want a concept to become inactive is that you'd have to maintain that logical definition. Sometimes the style of modeling in an area of SNOMED changes. We decide to, change the role groups around, or, do something. And all the concepts in the area of the hierarchy need to be updated. All the axioms need to be, transformed or reformatted so that they classify correctly. We don't do that with the inactive concepts. We just make the definition inactive. But we do create a semantic relationship between the inactive concept and some active concept to allow that link to happen. And that semantic relationship is called historical association, and it has a type. For example, the nicest and the cleanest type of historical association is same as, because it really means that these two concepts are completely equivalent. They can always be used like for like. There are some other, historical associations that are looser.
I think you should consider these historical associations just as a map, right? So you map the inactive concept to an active replacement. Okay, so I'm going to speak now to the process. So what we do when we inactivate the concept, the author will consider what is the reason why we're inactivating. Some will be inactivated because it's duplicate, because there's an error, because it's ambiguous. So if it's because it's duplicate, it will mean that there's one other concept that is the same. So we'll assign that with the same as association. So there is a reference set that's called the same as, and that goes for all those that are duplicate. If you have a concept that is ambiguous, when something is ambiguous, it may be because there are multiple interpretations. So then we create possibly equivalent to. Here in this slide, only one possibly equivalent to association, but often there will be more than one. And it's not it's not exhaustive necessarily. There may be something that's still lacking, right, in the some interpretation that could also exist but is not represented. So that's what, when you say a loose association, the possibly equivalent to is looser than the same as. If you want to be sure that it's exactly the same meaning, then it's a duplicate, and then it's the same as association. And what you can also be sure of is that what if one of those active acute asthma, for example, in the first example, what if that is inactivated? Then you have an association to a now inactive concept, but then that is also maintained. So we always maintain these historical associations so that those records in the historical association reference set will always link to an active concept, so that you can always do the queries. So with every release, we make sure that the targets are active.
Okay.
Yeah.
Okay. So with the history supplement and the ECL language, it's possible to select which historical associations you want. If you just want the bare minimum, then you only get the same as relationships, and you know the semantics are very sure. It's a duplicate. They can be treated like for like. We've defined 3 profiles. We've got the mod, which is kind of like the medium, and that includes the same as before. Also includes replaced, was a, and partially equivalent. And the last one is a maximum, and that includes all of these. And it also includes, or it includes everything in the historical association reference set. So it could be, possibly equivalent to, and there's some others.
This has to do with the level of precision and recall that you want, and it depends on your use case. So if you just want to extract a set of candidates for clinical trials, right, then you may just use the broad one. But if you have a very safety critical purpose, then you would probably just want the same as. And these are just 3 profiles that we have specified, and this shows what is included. If you, for example, wanted a query that included the same as and the WASA, let's say those 2, you can actually still construct an ECL. It's not very pretty, but you can do it. Yeah. But this is just these profiles is like a syntactic sugar to make it easy.
Yeah, they're like shortcuts for different sets of historical associations. So these can be used in the ECL language, used in the history supplement. They can also be accessed in the FHIR terminology server as an implicit concept map. That's another way. Or they could be accessed, in the RF2 files. They're published as reference sets. Okay, so that's history supplements. This is an example of where we use the history min, and we only use the same as relationships. We wouldn't get the allergic ineffective asthma. Let's move on to enabling preventative care measures. So this scenario is focused on the COVID pandemic and about improving the quality and efficiency of care for certain groups who might be most at risk of, some disease or some infection or some outbreak. So during the COVID pandemic, there were, large numbers of people who have the COVID virus. And some of the serious outcomes were COVID pneumonia, and a shocking proportion of people who contracted COVID pneumonia were not surviving. And there seemed to be various risk factors that the clinicians were noticing, and some of those were obesity, diabetes, and hypertension. And this is at a time when data was so important because no one knew the answers. It was a time of rapid research. So if we wanted to analyze some data, and we would obviously define a cohort of patients where they have the COVID virus detected. They've probably done a COVID test. And we could use some ECL to find the relevant concepts for that and then match the patient records, and that will be our cohort. And then we can drill down. We're sort of doing set theory here, aren't we? We're looking for patients who have got COVID pneumonia, and we probably want to define another group of patients who died. And then we want to do some more set theory to figure out, which conditions are having a worse effect or worse outcomes. So which comorbidities are most serious. So we can define a group of patients for obesity and just measure the correlation, of patients who died and patients who have COVID pneumonia. We could do the same for diabetes, and we could do the same for hypertension, high blood pressure. So we're going to do that now in the analytics tool. So this is the second function of the analytics tool, the patient group comparison, identifying patient groups who are particularly vulnerable to some condition. We've got another synthetic data set. It's just over 1 million patients. We're not interested in all of them for this cohort. We want the patients who have got COVID detected. So this isn't the disorder. This is actually just that they've got the virus and that they've had a positive COVID test. And that brings us down to around 450,000 patients. And the outcomes that we're interested in measuring are COVID pneumonia, I want E, UE. We're waiting for the terminology server to catch up. It's not working. Ah, there it is. There was any wrong result, so it's pre-selected it for me. And the finding is the patient died. So these are the two outcomes that we really want to measure against. And we can start, before we start building up patient groups and seeing who has the strongest correlation, we're going to look at the whole cohort, and we can run a report. So for the whole cohort of people who have just got COVID detected, the correlation of what percentage of people have COVID pneumonia is really high, nearly 27%, and the correlation of death again is very high, over 6%. Now we want to find the patient groups who are most vulnerable because we could create a different sort of care pathway for them or a different strategy for them. Maybe they get the vaccine first, or they're asked to stay at home, or at least made aware of the risks. So I'm going to create a patient group for the report, and I can add, however many requirements I want for patients in this group. And I'm going to start with diabetes. So again, that's created the ECL, any type of diabetes mellitus. And I'm going to give this group a label because it will show up in the graph. And I'm going to run the report. So that's had quite a dramatic effect on the patients who aren't in one of these patient groups, because the correlation of pneumonia has really shrunk. The correlation of death has shrunk really significantly as well. It's down to less than a third. And we can see that the patients in the group with diabetes have a nearly 40% correlation with pneumonia and 11% with death. I'm going to carry on and build up some more patient groups. We'll do hypertension. I'll give it a label. I want obesity as well. I don't want obese, do I? I want obesity. So I'm going to run the report again. And here we've got these groups, and they all have, really strong correlation with COVID pneumonia. And we seem to have found the patients who are most at risk of death, because we know that the patients who are not in any of these groups, have a tiny correlation. The tool's struggling to show the data because it's so small. It's less than 1%. So we can see that we've found the most vulnerable patient groups. And I suppose, we could go on and create patient groups that have combinations of these. But still, I think that illustrates the point. Any questions on this before I move on? Someone's going to ask about AI and predictions. And no? Okay. All right. Third scenario, this is the final one. Assessing treatments. How effective is each treatment option if multiple options are available? Our synthetic data set, again, has a large group of female patients who have had the BRCA1 gene mutation test. And this scenario is about what's the risk of developing breast cancer in this cohort, and how do the treatment options, how does taking each treatment affect the correlation with breast cancer? Obviously, a clinician will want to be able to give some advice and guidance on what to do in this situation when the patient feels they're at risk. And of course, the medical research has to happen behind the scenes to provide the guidance. So again, we're back to our set theory. We've got the blue cohort of patients, which is any female with a BRCA1 gene mutation. And then we have a few patient groups, patients taking some cancer preventative medicine, and the other group is patients not taking the medicine. And then we're going to look at the effect on the correlation of breast cancer. And we can see how these groups can be built up. The question is, how do I find the people with the BRCA1 gene mutation? And we want the concepts that are subtypes of the BRCA1 gene mutation. Sorry, this is like a positive test result. And this is the ECL query. For the breast cancer preventative medicine, there's not a good group concept in SNOMED CT for this, because there's a lot of different medications. Some of them are different in different countries. I looked at the UK guidance when I put this slide together about 2 or 3 years ago, and they were prescribing 3 different medicinal products, these 3 here. So for this one, we actually have to create a subset. We can't just pick some concept and say descendants. We have to have a more complex query. So it's products containing tamoxifen or anastrozole or raloxifene, and then we get all the relevant concepts for this. And then people with breast cancer is simple. So this is showing how we could do it in a traditional database to find patients with a malignant tumor of breast. We could go to, we kind of want to do something like this in SQL, although you can't, of course. We want to select patient IDs from some EHR table where a diagnosis is equal to malignant tumor of breast or some descendant. So in reality, you'd need to do an ECL expansion against a fire terminology server, get some set of concepts. Maybe you'd create a temporary table and do a join, something like that. In the demo tool, we've got like a document-based store. So we're using Elasticsearch, so we're doing it a bit differently. But that's the theory. All right, so we're going to go for the treatment comparison. Before we load the screen, we're going to look here at the subsets. So you'll notice on all the other screens, I was just typing in the name of some concept and then just getting all its descendants as well. But that's not going to work for the breast cancer preventive medicine. So we've created a subset here, just in the demonstration tool. It's not being published, but something that we can refer to. And we've got an ECL builder here, and we've picked up the descendants of each of these types of products. So we'll be able to use this breast cancer prevention subset. And we're going to the treatment comparison screen, and we're picking up the main hospital synthetic data set. And for the cohort, we're interested in females who have the BRCA1 gene mutation tested positive. Yeah, mutation detected. There's around 1,000 patients. And the outcomes we're interested in, there's only one. It's breast cancer, malignant tumor of breast. And I'm going to run the report with no patient groups to start with. And we can see that the correlation for this cohort is very high, it's nearly 50%. So then we're going to look at the treatment options, and we're picking the drug, the breast cancer preventative drugs, and it's a subset. And it's not working because I missed an R. And I'm going to give it a label.
So what we are selecting here is not a concept. It's, as you see, there is in the brackets, it says subsets. So we're actually referring to the subset that Kai was just showing in the other screen before.
And we can run the report again. And we see that the correlation for patients in this group who are taking the preventive medicine is less, it's 30%. And we can see that that's had the effect that the patients not taking the medicine, because they're not in this group, have gotten a much stronger correlation that's shot up to around 73%. So I think this tool probably can't be used for clinical decision making. It's obviously a demonstration tool. It's not very scientific, really. We've just got some graphs, and it helps convey what's possible with SNOMED and how easy it is to do ad hoc selections over the hierarchy and measure correlations. But I suppose it could be used to do some initial exploration of the data and maybe form some hypothesis for proper clinical study. And that's what the last slide is about in this section, interpreting the results. Yeah, please.
Thank you. So it's maybe not directly related to the demo, but I was wondering if there is some recommendations within SNOMED CT to represent negations of concepts, or like the absence of a particular concept. And I have a similar question for time. If there is modifiers, there is probably modifiers for time, like a treatment during the childhood or something like that.
It's a great question. That we've got a project going at the moment, actually, about negation and representing situations, because it's not easy to represent negation properly in SNOMED CT. We do have some situation concepts that talk about negation, no history of smoking, these things. We're not completely satisfied with the representation. And from our perspective, the OWL reasoner isn't reasoning with negation. It's not part of our OWL profile, so we can't do it. So the high level recommendation is to store negation probably in the record, as part of the file profile, rather than doing it with SNOMED CT. It's better to record, for example, with the no smoking, to record smoking. That's what the SNOMED is good for, and then record the negation elsewhere in the record.
It's also a matter of, considering the role of SNOMED CT and how much to take on in SNOMED. I'm thinking about if we were to have like the absence of every disorder. It's like having mirroring the disorder hierarchy and then with a corresponding negated version of it. So it would be like a combinatorial explosion if we want to also have all the family history and so temporal context and family contexts and all of that. So this is really where the balance between what goes in the terminology, what goes in the information model. But we also acknowledge that not all information model can capture all the details. Some of the new modern information models that are applied, they do it very well. But we are also seeing implementations where we are where they rely on being able to express that there's an absence of fever or no family history of cancer. So the situations hierarchy in SNOMED CT allow us to have concepts. So if you go into the browser and look at situations, you'll find that there are some of the concepts that have this contextual information included, but the situations is a specific hierarchy where we can express that. And the concept model for that hierarchy includes things like, is it absent, is it present, who is the subject? It's not the patient, it's a family member, and it was not now, it was yesterday. So there are different, there are those three different axes you can say that we can modify aside from the main procedure or finding.
Yeah, but the general recommendation is to store it in the information model if you can. Yeah. I have to show this slide because not everyone has training in statistics and data science. Of course, correlation does not equal causation. There can be alternative explanations for the results. And examples of common factors that can influence the outcomes of these types of reports are existing conditions, which you may not have been considering when you ran your report, patient lifestyle, family history, age, genetics, drug interactions. So unless you include all these things on your report, you may be getting very skewed results. So something to bear in mind. So yeah, the tool that I showed is really good for exploring data and starting to form a hypothesis. But yeah, you need to be thorough and go through the alternative influences. All right, I've come to the end of that slide. Is there any other questions? There's various links here, which we've shown already, the ECL guide. This is down here, it's no lytical. This is a link to the GitHub project for the tool I just showed.
What is needed to access to Snolytical? Is it with our ID from Confluence or something like that?
We're not able to provide a hosted version, but there's instructions in the GitHub website how to set it up on your machine. That's recommended. We've also got a YouTube video from a year or so ago in Portugal where we did a workshop with a bunch of people and we all set it up in real time, so we had it running on everyone's machines. Yeah, if you want to play with it, we could always have a call and you can play around.